In today's video, here is a nice problem. It's coming from the Japanese Mathematics Olympiad, edition 2004. Here is the following setup. Prove that there is no positive integer n such that we have these three conditions. We have 2n plus number 1 and 3n squared plus number 1 and 6n squared plus number 1 are perfect square. Okay? So our goal, we are going to show there is no solutions for this equation if you have this condition, this one and this one and this one as a perfect square. Okay? So I'm going to prove this one in two different ways. First of all, I'm going to use the congruence notion. The other method, I'm going to use the Peel's equation. Okay? Maybe there is more methods you can apply. You guys, you can give the hands to this problem prior getting the solution. Go ahead, pause this video when you come back for a solution. Okay? Now let's go through this one. So we are assigning these three terms as a perfect square, which means we have 2n squared plus number 1 equals x squared, and also I have 3n squared plus number 1 equals y squared. Finally, I get 6n squared plus number 1 is a perfect square. Okay, z square. So now the first thing is coming to our minds. We are going to get a root of n. Okay, we are going to cancel n from this one to write the three equations in terms of x, y, and z. Okay, let's take this equation multiplied by number 2, then subtract both equations. Okay, so for this equation becomes 6n squared plus number 2 here equals 2y squared. Then I'm going to leave this equation as it is. Also, I'm going to make this one on this form by multiplying both sides by 3 in order to get 6n squared as well here. Okay, so I get here 6n squared plus number 3 equals 3x squared. Okay, then taking this equation minus this equation, okay, I get here 6n squared cancelled out. I will be left with 2 minus 1, which is number 1, equals 2y squared minus z squared. Okay, just I'm going to switch these two terms to put my sign here. I get z squared minus 2y squared equals number 1 equals minus number 1. Here is the Peel's equation. Okay, so since we get to this expression, so I'm going to apply the Peel's equation first in order to show this one. Then we'll move on to the next method. So because we already get this expression is written on the form of Peel's equation, so we are going to take this advantage and solve this equation simply, then conclude the other solutions. Okay, so this is just first equation. Let's look for the other equation. For the second equation, I'm simply going to take this equation minus this equation. I get here 6n squared cancelled out, 3 minus 1, which is 2. I get 3x squared minus z squared. Okay, I get two nice expressions here. So this equation is a Peel's equation. This one is not a Peel's equation. Okay, because as you know, the Peel's equation is always written on this form: z squared minus d y squared equals, in fact, Peel's equation is written on this form, n. What is it? N is an integer. Okay, so we are taking the n as a special case. We put it 1 or plus or minus number 1. Okay, so usually we're dealing with the case when we have number 1 here. So there is a certain cases if n is not equal to 1, you still can solve the equation as well. Okay, now let's work out with this one. So it's simply, I'm going to find the solution for this one, then take those solutions and insert them in the second equation to see if both equations are satisfied the solutions or not. Okay, first of all, the obvious solution for this one, as we know, is a z0, which is number 1, and y0, which is minus number 1. which is 1. Okay, you still have plus or minus because of square here. So, but we don't care about this one. Which we care about, we are going to find the contradiction. That's mean we have no solutions for this one. Okay, so this is a base solution. If you plug this solution, you get you to z square here, you get you number 1, then you cancel number 1 from both sides, you get 6n square equals 0, and equals 0, which is impossible because we are dealing with a positive integer. But let's make it more better to go a little far from the origin, just to find another solution for the Peel's equation. So another solution, if you apply the recursion here, the recursion is the solution of the Peel's equation is going to be written on this form: z plus square root of 2y equals z0 plus square root of 2y0 to the 2n plus number 1, plus or minus. Okay, we previously solved the Peel's equation. If you want to take a look at the previous video, which I did before. Oh, anyway, the proof is easy to prove this one. We are not going through the proof because we still have a lot of work to do. So I'm going to apply right away this formula, which is recursion. Okay, so to find the solutions for this equation is depending on n. Okay, if you plug n with number 0 here, you get obvious solution here. Okay, because this one is going to be written in this form: this is 0, which is 1 plus square root of 2 to the n plus number 1. Okay, we still have plus or minus here. As you plug in n with the new number, you get a new solution. Okay, let's go to the new solution after this one. Okay, let's replace n with number 1. So I get here 1 plus square root of 2 cubed, okay, as I have here, equals 1 plus square root of 2 quinary square is multiplied by 1 plus square root of 2. Okay, so this one is giving us 1 plus 2, which is 3, plus 2 square root of 2 is multiplied by 1 plus square root of 2. So if you multiply this one is giving us 3 plus this 4 here, which is 7, plus 2 square root of 2 plus 3 of square root of 2, okay, which is 5 square root of 2. So this is the solution for the Peel's equation. The second solution, 1 equals 7 and y1 equals 5. Okay, now if you try to plug this one here, you get 7 square, which is 49, minus 5 square, which is 25, is multiplied by 2, which is minus 50. You get 49 minus 50, which is minus number 1, which is a solution for this equation. Okay, now I'm going to take this fact of the solution and insert it back to this equation. So I get here the following: I get 2 equals 3x squared. Z will be replaced with number 7, which is 49. Then moving over this 49 to the left, I get here 51 equals 3x squared. Okay, so dividing both sides by 3, you get 17. This one is given as x squared is 17. But this one is not a perfect square. We see it's clearly it's a contradiction. Okay, we shouldn't go any further because the other solutions, they are not going to satisfy this equation as well. So I have the same thing here. If I'm going to plug this one here, I get 3n squared plus number 1 equals y squared. Y squared, which is 5 squared, which is 25. Simply going to move over this number 1 to the right, I get 3n squared equals 24. Dividing both sides by number 3, I get n squared equals 8. Is not a perfect square. Okay, even this equation is not going to satisfy it. Okay, now we have proven this one. Let's move on to the next method where we can use a congruous notion. Okay, so previously we have shown this equation in terms of x and y and z. Now we are going to use the same equation that I had before in order to prove this one. So by reducing this one to the mod something. So I'm going to first table, I'm going to show x squared or y squared or z squared as a perfect square is a congruent to 0 or 1 mod 4. Okay, so we know 0 squared is the same 0 squared mod 4. We know y squared is the same as 1 square mod 4. We know 2 square, which is 4, which is 0 mod 4. We know 3 square, which is 9. 9 is 1 more 8 mod 4. So this one, just we are dividing the number by number 4 to see what's the remainder when we square it. Always you get a remainder 0 or 1 as you divide in by number 4. You take the integer, whatever the integer, and square it and divide by number 4. Then you will see the remainder of this one 0 or 1. Okay, so we get here 0 1 mod 4. The same thing when we get 4 square here, we get 0 mod 4 because 4 divides 16. So when you get even number, you get 0. When you get an odd number, you get number 1. Okay, this one is going to be always on the same pattern. Now we are going to use this advantage and apply it here. Again, z square equals to y square minus number 1. Also z square equals to y square minus number 1. Okay, now I'm going to use this fact to determine the parity of y. So it seems a little confused to determine the parity of y. We know the parity of z, which is odd. This one is odd, but we don't know this one. So by the way of contradiction, we are going to determine the parity of y. So by the way of contradiction, suppose y is odd. Let's set y equals to c plus number 1. Taking this value of y and insert it back into this equation, I get z square equals to, I get 2c plus number 1, quantity square minus number 1. Okay, distribute this one out, I get 4c square, which is 8c square, plus 4c, which is 8c minus number 1. Okay, if you go back to this equation here, we have z is odd because this one is even plus number 1, which is odd. We know based on this information that we found by using the congruence, by reducing this to mod 4, we get, when you have odd integer, you get a remainder number 1. When you get an even integer, we get remainder number 0. So this one is telling us this one is a congruent to 1 mod 4, since we have this one is odd. Now this one is 0. This one is 0 because 4 divides this one, 4 is this one. I will be left with minus number 1 is a congruent to 1 mod 4, which means minus 2 is a congruent to 0 mod 4. This one, it's clearly is a contradiction. 4 cannot divide 2 because 2 over 4 is not integer. Okay, so I have proven this one. It wasn't odd. That means y must be even. Okay, so since we found y is even, so it's clearly, let's set, I'm going to do the same thing that I did before. Let's set y equals to d. Okay, plug in this one into the same equation that I have z square equals to y will be replaced with this one, which is 2d quantity square minus number 1. This one I'm going to distribute. This one is giving us 4 8d square minus number 1. As I said before, I'm going to reduce this one to mod 4. So when you get a remainder number 1 because it's odd, as I have previously. So taking this number 1 to the left, I get 8d square minus 2 is a congruent to 0 mod 4. This one is 0. This one is 0. This one is telling us 4 divides 2, which it's clearly it's a contradiction because the divisor is bigger than this one. Okay, this one must be in numerator, this one must be in denominator. So we have numerator smaller than denominator. Okay, which is impossible, which is not integer, which is a contradiction. So we have proven this one by using this way.